Light. It paints our world with color. It carries information across the vastness of space. And now, we're learning to manipulate it in incredible ways. Imagine a material that can filter light with pinpoint accuracy. Picture it sorting the colors of the rainbow, letting only the chosen few pass through. This isn't science fiction. This is the promise of copper-loaded phosphate glass. This remarkable material holds the key to revolutionizing optics. From capturing breathtaking images to developing life-saving medical devices, the possibilities are endless. But to understand its potential, we first need to delve into the fascinating world of glass. Not just any glass, mind you, but phosphate glass. Phosphate glass is different. It's a unique material with properties that make it ideal for hosting copper ions. And it's these copper ions that give the glass its remarkable light-filtering abilities. Join me as we explore the science behind this groundbreaking material. We'll uncover its secrets and discover how it's poised to reshape our world. Glass. It's all around us. But we rarely stop to consider its wonders. It's transparent, fragile, and yet surprisingly strong. But phosphate glass is in a league of its own. Unlike the common soda-lime glass, phosphate glass boasts a unique structure. This structure, with its phosphorus and oxygen network, makes it incredibly versatile. Think of it as a molecular scaffold. This scaffold can accommodate a variety of elements, each adding its own special properties. And when it comes to manipulating light, copper is the star of the show. Copper ions, nestled within the phosphate glass matrix, act like tiny antennas. They interact with light waves, absorbing specific wavelengths and letting others pass through. But how do we get the copper into the glass? It's a delicate dance of heat and chemistry. Researchers carefully introduce copper oxide during the glass-making process. The heat persuades the copper oxide to share its copper ions with the molten glass. The result? A beautiful, transparent material with a hidden talent, the power to control light itself. Creating copper-loaded phosphate glass is a bit like baking a cake. You need the right ingredients in the right proportions, mixed and baked to perfection. In this case, our ingredients include phosphorus pentoxide, a glass former, and copper oxide, our light-manipulating secret ingredient. These ingredients are carefully measured and heated to incredibly high temperatures. As the mixture melts, the copper oxide breaks down, and copper ions disperse throughout the molten glass. It's like adding sprinkles to cake batter, ensuring they're evenly distributed. Once the mixture is homogeneous, it's carefully cooled, allowing the glass to solidify. The result is a solid, transparent material imbued with the light-filtering properties of copper. But the story doesn't end there. Scientists put this copper-loaded glass to the test, exposing it to gamma radiation. This isn't just about making the glass tough, it's about understanding how its optical properties change under such conditions. Because in space, in medical devices, the material needs to perform even under harsh conditions. Section 4. Unlocking optical secrets. Gamma radiation is a powerful force. It's invisible, energetic, and can alter the very structure of matter. So how does our copper-loaded phosphate glass stand up to this challenge? Surprisingly well, as it turns out. Researchers found that gamma irradiation actually enhances the optical properties of the glass. It's like the radiation unlocks hidden potential, making the glass even more effective at filtering specific wavelengths of light. Imagine taking an already impressive photograph and making it even more vibrant and clear. This discovery has significant implications for a wide range of applications. In imaging, it could lead to cameras with unprecedented sensitivity and clarity. In lasers, it could pave the way for more precise and efficient light sources. And in medical diagnostics, it could enable the development of new imaging techniques. The future of optics is bright thanks to the unique properties of copper-loaded phosphate glass. Section 5. Illuminating the future. The potential of copper-loaded phosphate glass extends far beyond the laboratory. This remarkable material is poised to revolutionize numerous industries, from telecommunications to healthcare. Imagine a world with faster, more reliable internet connections. Copper-loaded phosphate glass can make that a reality by reducing signal loss in optical fibers. This means data can travel farther and faster, improving communication across the globe. Now, picture doctors using advanced imaging techniques to diagnose diseases earlier and more accurately. Copper-loaded phosphate glass can help make that happen by enabling the development of new medical imaging devices. These devices could provide clearer images of the human body, leading to better diagnoses and treatment plans. But the impact of this material goes beyond technological advancements. It also has the potential to create new jobs and boost the economy. As demand for copper-loaded phosphate glass grows, so too will the need for skilled workers to manufacture and utilize it. This is just the beginning. As research continues, we can expect even more exciting applications for copper-loaded phosphate glass to emerge, illuminating the path toward a brighter future. Hey there, welcome to the For Science Salah Lotfy channel. Today we're diving into an intriguing study on gamma-irradiated cadmium phosphate glass modified with copper oxide. This unique material could revolutionize optics and radiation shielding. This research, published in Materials Chemistry and Physics, was conducted by Associate Professor Dr. Omnia Ibrahim Sallam and Professor Dr. Fathy Ezz-Eldin from the Radiation Chemistry Department, National Center for Radiation Research and Technology in Cairo, Egypt. Corresponding author Dr. Ahmed Abdeldaim from the Radiation Physics Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt, also contributed significantly to this groundbreaking work. So, what's this study all about? Phosphate glass is known for its unique optical and electrical properties. In this study, researchers synthesized cadmium phosphate glass modified with 0.5% copper oxide and exposed it to gamma radiation at various doses. Their goal was to analyze how radiation affects the structural and optical properties of the glass. Let's jump into the key findings. First, X-ray diffraction confirmed that the glass remained amorphous, meaning it didn't crystallize under radiation. This is crucial for maintaining its unique properties. Infrared spectroscopy showed changes in the phosphate and copper oxide bonds, indicating structural modifications. Optical analysis revealed that increasing gamma radiation reduced the optical band gap, altering how the material interacts with light. These changes make the glass suitable for optical filters, radiation shielding, and advanced imaging applications. Now, why is this important? This research has significant applications. For advanced optical filters, the modified glass can selectively filter light, improving imaging quality. In radiation-resistant materials, it's useful for shielding in high-radiation environments like nuclear facilities. And for laser and sensor technologies, it has potential applications in medical imaging, laser systems, and optical sensors. The study of gamma-irradiated phosphate glass opens new doors for optical and radiation-resistant materials. If you're as fascinated by cutting-edge scientific research as I am, make sure to hit that subscribe button and join the For Science Salah Lotfy channel community. Thanks for watching and stay curious. Imagine a world bathed in invisible light, a light so powerful it can alter the very structure of matter. This is the world of gamma rays, the most energetic form of light in the universe. Born from the heart of exploding stars and the maelstroms around black holes, gamma rays possess incredible energy. For decades, scientists have harnessed this power, using gamma rays to sterilize medical equipment, unlock the secrets of ancient artifacts, and even treat cancer. Now a new chapter in the gamma ray story is being written, one that promises to revolutionize fields as diverse as telecommunications, energy, and medicine. This revolution centers around a seemingly simple material glass. But not just any glass. This glass is infused with the elements cadmium and copper and then bombarded with gamma rays. The result is a material with remarkable new properties, poised to transform industries and redefine what's possible. This is the story of gamma-irradiated cadmium phosphate glass, a testament to the power of human ingenuity to harness the universe's most extreme forces for the betterment of humankind. Glass. It's a material we often take for granted, yet its history stretches back millennia. From the ancient Egyptians who shaped it into dazzling beads to the stained glass windows of medieval cathedrals, glass has always captivated our imaginations. Today, glass is more than just a beautiful material, it's a technological marvel. We rely on it for everything from the screens of our smartphones to the fiber optic cables that carry information at the speed of light. Among the many types of glass, phosphate glass stands out for its unique properties. Highly transparent and possessing excellent thermal stability, phosphate glass is like a blank canvas for scientists and engineers. Adding cadmium and copper to the mix enhances its optical properties, making it ideal for applications where precise control of light is essential. It's this unique blend of properties that makes cadmium phosphate glass so alluring for applications that demand the utmost precision and performance. Gamma rays are like tiny architects capable of rearranging the very building blocks of matter. When gamma rays interact with cadmium phosphate glass, something incredible happens. Imagine these rays as subatomic bullets, each carrying a packet of energy. As they collide with the atoms within the glass, they knock electrons out of their orbits, creating what scientists call electron-hole pairs. These electron-hole pairs don't just disappear, they trigger a cascade of events within the glass's structure. Atoms shift positions, chemical bonds break and reform, and the entire material undergoes a profound transformation. Think of it like shaking up a snow globe. Before the shake, everything is static. Afterward, the snowflakes settle into a new, different pattern. Gamma irradiation does something similar to the glass, altering its optical, electrical, and even mechanical properties. Section 4. Unveiling the Secrets. Dr. Sallam's groundbreaking research. At the National Center for Radiation Research and Technology, a team of scientists led by the brilliant Dr. Omnia Ibrahim Sallam embarked on a journey to unravel the mysteries of gamma-irradiated cadmium phosphate glass. Their meticulous research involved subjecting samples of this glass to varying doses of gamma radiation. Like chefs experimenting with a new recipe, they carefully controlled the irradiation time and intensity, eager to understand how these factors influenced the glass's transformation. Using sophisticated instruments, Dr. Sallam's team analyzed the irradiated glass, carefully measuring its optical properties, including its ability to absorb and transmit different wavelengths of light. They delved into the atomic structure of the glass, using techniques like X-ray diffraction and electron microscopy to observe the subtle rearrangements caused by the gamma rays. Their findings were nothing short of groundbreaking. The gamma irradiation had a profound impact on the glass's optical properties, enhancing its ability to filter specific wavelengths of light. This discovery opened up exciting possibilities for using this material in a wide range of optical applications. Section 5. A world of applications from lasers to radiation shielding. The unique properties of gamma-irradiated cadmium phosphate glass make it a game-changer in a multitude of fields. Imagine lasers that are more powerful and efficient, capable of performing intricate surgeries with greater precision. Gamma-irradiated glass can make this a reality by serving as a crucial component in optical filters, ensuring that only the desired wavelengths of laser light pass through. In the realm of telecommunications, this remarkable material could lead to faster and more reliable data transfer. Fiber optic cables, the backbone of our internet age, rely on glass fibers to transmit information. Gamma-irradiated glass with its enhanced optical properties could significantly boost the speed and bandwidth of these networks. And for those working in hazardous environments, gamma-irradiated glass offers a new level of protection. Its ability to absorb harmful radiation makes it an ideal material for shielding against X-rays and gamma rays, protecting medical professionals, nuclear workers, and even astronauts on missions beyond Earth's protective atmosphere. Section 6. The future is bright economic and scientific implications. The groundbreaking research of Dr. Sallam and her team has far-reaching implications, promising both scientific and economic benefits. On the scientific front, this discovery opens up new avenues of research in materials science and photonics. Understanding how gamma rays interact with matter at the atomic level could lead to the development of entirely new classes of materials with tailored properties. Economically, the potential is vast. The enhanced optical properties of gamma-irradiated cadmium phosphate glass make it a valuable material for a wide range of industries. From telecommunications and laser technology to medical imaging and radiation protection, this material has the potential to drive innovation and create new jobs. Section 7. Beyond the Horizon, a universe of possibilities. The story of gamma-irradiated cadmium phosphate glass is a testament to the power of scientific curiosity and the ingenuity of the human mind. What began as an exploration into the interaction of light and matter has blossomed into a field with the potential to reshape industries and improve lives. As we stand on the cusp of this new era of material science, one thing is certain: the future is bright. With each new discovery, we unlock a deeper understanding of the universe and our place within it. And with each technological leap, we move closer to a future where the seemingly impossible becomes possible. The journey of exploration and discovery is never-ending. As we continue to probe the mysteries of the cosmos, we can be sure that more wonders await, waiting to be unveiled by the intrepid minds of scientists like Dr. Sallam and her team. The future belongs to those who dare to dream big, to explore the unknown, and to harness the power of the universe for the betterment of humankind. Hey, science enthusiasts! Welcome back to the For Science Salah Lotfy channel. Today, I'm diving into the fascinating world of gamma-irradiated cadmium phosphate glass. Sounds like a mouthful, right? But trust me, it's super cool. First up, let's talk about how this glass is made. Picture this, a precise mix of 90% phosphorus pentoxide and 10% cadmium oxide, with a dash of 0.5% copper oxide. They melt this mix at a scorching 1000 to 1100 degrees Celsius for 2 hours. Then it's poured onto a preheated stainless steel plate and annealed at 400 degrees Celsius, slowly cooling to cut down thermal stress. Science in action, but wait, there's more. To really test its metal, this glass gets hit with gamma rays. Picture a high-tech setup with an Indian 60 degrees Celsius gamma cell, exposing the glass to doses ranging from 5 to 30 kGy. It's like giving the glass a superhero origin story. Now onto the testing phase. Brace yourselves for some serious science. First, X-ray diffraction, XRD, checks if the glass stays amorphous, no crystals here. Then, Fourier transform infrared spectroscopy, FTIR, steps in, pinpointing any changes in chemical bonds caused by radiation. Next, UV visible spectroscopy measures how the glass absorbs and transmits light. Electron paramagnetic resonance, EPR, detects defects and copper-ion interactions. Ultrasonic testing evaluates the glass's elastic properties and internal structure. Differential scanning calorimetry, DSC, checks its thermal stability up to a sizzling 650 degrees Celsius. And finally, micro-hardness testing assesses its mechanical strength. Phew! So, what's the big takeaway? This research shows that gamma irradiation can tweak the properties of copper-doped cadmium phosphate glass, making it a strong candidate for optical filters and radiation shielding. Who knew glass could be so versatile? If you're as pumped about this as I am, be sure to like, share, and subscribe to For Science Salah Lotfy channel. Stay tuned for more mind-blowing scientific discoveries. Catch you next time! Hey there, science fans! Today, we're diving into the fascinating world of glass. Not just any glass, but a special kind that's been zapped with gamma rays. Now, before you picture a glowing green substance like something out of a comic book, let me assure you, it's not that dramatic. However, what happens at the microscopic level is truly mind-blowing. We're talking about cadmium phosphate glass doped with copper oxide. Think of it like this. Imagine a delicious chocolate chip cookie, the glass, with tiny bits of orange zest mixed in, the copper oxide. Now we expose this cookie to gamma rays, which are like super-duper high-energy light beams. This exposure changes the cookie's structure and properties, making it useful for some really cool applications. These special glasses are like chameleons of the material world. Gamma irradiation gives them the power to transform their optical and structural properties, making them incredibly valuable in fields like optics and radiation shielding. Intrigued? Let's get our geek on and explore. So how do we know what's going on inside this irradiated glass? Well, scientists have a secret weapon: X-ray diffraction. This technique is like giving the glass a super-powered X-ray scan to see its internal structure. You see, atoms in a material are arranged in specific patterns. X-ray diffraction helps us identify those patterns, revealing whether a material is crystalline, highly ordered, or amorphous, lacking long-range order. In our case, the X-ray diffraction results tell us that cadmium phosphate glass, even after being exposed to gamma rays, remains amorphous. It's like the cookie dough maintaining its random structure even after baking. This amorphous nature is crucial for its transparency and ability to interact with light in unique ways. Next up, let's talk about FTIR spectroscopy, a fancy name for a technique that helps us identify the different types of chemical bonds present in our glass. Think of it like taking fingerprints of molecules. FTIR spectroscopy works by shining infrared light on the glass and analyzing how much light gets absorbed. Different types of chemical bonds vibrate at specific frequencies like tiny tuning forks. When the frequency of the infrared light matches the vibrational frequency of a particular bond, it gets absorbed, creating a distinct pattern in the spectrum. By studying these molecular fingerprints, we can understand how the chemical bonds in the glass are affected by gamma irradiation. Are they weakened, strengthened? Do new bonds form? It's like solving a molecular puzzle. Section 4. A colorful transformation. how gamma rays change optical properties. Now for the fun part, color. Remember how gamma rays are like supercharged light beams? Well, when they interact with the glass, they can actually change its color. That's because the way a material interacts with light, absorbing and reflecting different wavelengths, determines its color. Gamma irradiation can alter the electronic structure of the copper oxide within the glass, changing the way it absorbs and reflects light. This can lead to fascinating color shifts, making the glass appear darker or even change its hue entirely. It's like magic, but with science. Section 5. Blocking the unwanted understanding bandpass filters. This color-changing ability isn't just a cool party trick, it has some seriously useful applications. Remember how we talked about the glass acting like a chameleon? Well, by controlling the gamma irradiation, we can fine-tune the wavelengths of light that the glass absorbs and transmits, essentially turning it into a bandpass filter. Imagine a bouncer at a nightclub, only allowing people of a certain age to enter. That's what a bandpass filter does with light. It selectively allows only a specific range of wavelengths or colors to pass through while blocking others. Section 6. Tougher than it looks. Mechanical and thermal stability. Now you might be thinking, all this is cool, Bill, but is this irradiated glass fragile? Great question. We need to make sure our superglass can withstand the rigors of real-world applications. That's where mechanical and thermal stability come in. Scientists use various tests to assess the glass's toughness and durability. Microhardness testing measures how resistant the glass is to scratching and indentation. Like when you accidentally drop your phone, we've all been there. DSC, or differential scanning calorimetry, analyzes how the glass behaves when heated or cooled, ensuring it doesn't crack or melt easily. And for the grand finale, ultrasonic velocity tests. These tests use sound waves to determine the glass's elastic properties and detect any internal defects. The goal is to make sure our gamma-irradiated glass is tough enough to handle whatever life throws at it. Hey there, science fans! Today, we're diving into the fascinating world of gamma rays and their impact on something called cadmium phosphate glass. Now you might be wondering, what are gamma rays, and why should we care about their effects on glass? Gamma rays are like superpowered beams of light, invisible to our eyes. They're part of the electromagnetic spectrum, just like the light we see, but with way more energy. Think of them as tiny energy packets, or photons, zipping around at the speed of light. Now, cadmium phosphate glass isn't your everyday window pane glass. This special type of glass is made by mixing cadmium oxide and phosphorus pentoxide at high temperatures. It's got some really cool properties that make it useful for things like lasers and special lenses. But what happens when these powerful gamma rays meet our special glass? Buckle up, because things are about to get interesting. We'll explore how these rays can actually change the glass's properties, making it behave in surprising ways. Let's go. Remember those gamma rays are tiny energy packets? Well, when they hit the cadmium phosphate glass, they can knock some electrons out of place. This knocking out process is what scientists call ionization. It's like a tiny game of billiards inside the glass, with gamma rays as the cue ball. This ionization can cause some pretty amazing changes in how the glass interacts with light. One of these changes is in something called the optical energy gap. Think of this gap as the amount of energy needed for light to pass through the glass. Gamma rays can actually make this gap wider. This means the glass can block certain colors of light after being exposed to gamma rays. Another cool change happens to the refractive index. This fancy term basically describes how much light bends when it enters the glass. You know how a straw looks bent when you put it in a glass of water? That's refraction in action. Gamma rays can actually change the refractive index of cadmium phosphate glass, making light bend differently after passing through it. These changes in how the glass interacts with light are super important for scientists. They help us understand how gamma rays affect materials at a fundamental level. Plus, they open up possibilities for using this irradiated glass in new and exciting ways. Okay, so we've seen how gamma rays can affect how light interacts with cadmium phosphate glass. But what about the glass's structure itself? Does it stay the same, or do those powerful rays shake things up a bit? You guessed it. Gamma rays can actually change the very structure of the glass. One way they do this is by affecting the glass's density. Density is how tightly packed the atoms are inside a material. Imagine a box full of marbles. A denser box would have more marbles packed into the same space. Gamma rays can either increase or decrease the density of cadmium phosphate glass, depending on the intensity and duration of the exposure. This change in density is directly related to another property called molar volume, which is basically the amount of space 1 mole of a substance takes up. So, how do gamma rays achieve this density and molar volume magic? Well, it all comes down to something called defect formation. You see, when those energetic gamma rays knock electrons around inside the glass, they can create tiny imperfections in the otherwise ordered arrangement of atoms. These imperfections are the defects. These defects might be small, but they can have a big impact on the glass's overall structure, leading to the changes in density and molar volume we discussed. It's like adding a few extra puzzle pieces to a nearly complete puzzle. It might not seem like much, but it can definitely shake things up. We've talked about gamma rays creating these tiny imperfections called defects in the glass. But how do scientists actually see these defects? They're far too small to be seen even with the most powerful microscopes. This is where a clever technique called electron paramagnetic resonance, or EPR for short, comes into play. Think of EPR as a sort of detective tool that helps scientists uncover the secrets hidden within the irradiated glass. Here's how it works. Remember those electrons that get knocked out of place by gamma rays? Well, some of these electrons end up trapped within the glass's structure, often near those defects we talked about. EPR uses magnetic fields and microwaves to interact with these trapped electrons, like sending out a signal and listening for a response. By analyzing the signals from these trapped electrons, scientists can learn a lot about the defects themselves. They can determine the type of defect, its concentration, and even its location within the glass structure. It's like using a metal detector to find hidden treasure, except our treasure is valuable information about the effects of gamma rays. EPR is a powerful tool that allows scientists to study the impact of gamma rays on materials at a very detailed level. By understanding these defects, we can gain insights into how radiation affects the properties of materials and potentially even find ways to control these effects for beneficial applications. We've seen how gamma rays can change the optical and structural properties of cadmium phosphate glass. But what about its mechanical properties? In other words, how does gamma irradiation affect the glass's ability to withstand force and pressure? One crucial mechanical property is elasticity. Think of a rubber band. When you stretch it and let go, it snaps back to its original shape. That's elasticity in action. However, if you stretch it too far, it breaks. Gamma rays can actually change the elasticity of cadmium phosphate glass. This means that after irradiation, the glass might become more brittle or more flexible, depending on the dose of gamma rays and the composition of the glass itself. These changes in elasticity are directly related to the structural changes we discussed earlier, particularly those pesky defects. Remember how gamma rays can create imperfections in the glass's atomic arrangement? Well, these defects can act like weak points in the material's structure, making it more susceptible to breaking under pressure. Understanding how gamma rays affect a material's elasticity and strength is crucial for many applications. For example, if we want to use irradiated glass in environments with high radiation levels, we need to know how it will hold up under these extreme conditions. Space is vast. It's full of mysteries. One mystery is gamma rays. These powerful rays come from exploding stars and black holes. On Earth, we can create gamma rays. We use them to study materials. One material is glass. Glass seems fragile, but it's tougher than we think. We're using gamma rays to learn about a special glass. It's called Q-doped CD phosphate glass. This glass is special because we added copper to it. Copper changes how the glass behaves. Gamma rays help us see these changes. It's like we're looking inside the glass with a super-powered microscope. By studying this glass, we learn about the universe, we learn about radiation, and we learn how to make better materials. Materials that can survive the harsh conditions of space. Materials that can improve our lives on Earth. Everything in the universe bends and stretches, even things that seem solid, like glass. We call this ability to change shape elasticity. It's what makes a rubber band snap back, or a diving board spring back up. Gamma rays can change a material's elasticity. They do this by rearranging the atoms. Imagine the atoms are tiny balls connected by springs. Gamma rays are like invisible fingers. They can stretch or compress the springs. When gamma rays hit our special glass, something amazing happens. The glass becomes more elastic. This is because the copper atoms are moving. They are finding new places within the glass structure. These new positions allow the glass to bend and stretch more. We use something called Poisson's ratio to measure elasticity. It tells us how much a material stretches in one direction when squeezed in another. Imagine a marshmallow. Squeeze it between your fingers. It gets thinner but longer. That's Poisson's ratio at work. Gamma rays can change Poisson's ratio. In our special glass, they make it higher. This means the glass becomes more compressible. It's like the marshmallow, easier to squeeze. Hardness is another important property. It tells us how resistant a material is to scratching or denting. Gamma rays can also affect hardness. In some cases, they make materials harder. In other cases, they make them softer. Section 4. A spectrum of change, how gamma rays paint the glass. Gamma rays are invisible, but we can see their effects. One way is by looking at how they change a material's color. Color is just light. Different colors have different energies. When light hits a material, some of it gets absorbed, the rest gets reflected. The reflected light is what we see as color. Gamma rays can change the way a material absorbs light. This can change its color. In our special glass, gamma rays make it darker. This is because the copper atoms are absorbing more light. The gamma rays are changing the energy levels of the copper atoms. This makes them better at trapping light. We use a tool called a spectrophotometer to measure these changes. It tells us how much light is absorbed at each wavelength. This gives us a fingerprint of the material. By comparing the fingerprint before and after gamma irradiation, we can see how the material has changed. Section 5. EPR analysis. Listening to the whispers of atoms. Atoms are like tiny magnets. They have a property called spin. Spin can be up or down. When all the spins are aligned, the material is magnetic. But most materials have random spins. This means they're not magnetic. Gamma rays can flip the spin of atoms. This is where EPR comes in. EPR stands for electron paramagnetic resonance. It's a technique that uses microwaves and magnetic fields to study the spin of electrons. By using EPR, we can see how gamma rays affect the spin of atoms in our special glass. We can see which atoms are affected, and we can see how their spin changes. This tells us about the structural changes happening within the glass. Section 6. The heat is on. Thermal stability and glass transitions. Temperature is a measure of how much atoms are moving. The hotter something is, the faster its atoms are vibrating. At a certain temperature, solids melt into liquids. This is because the atoms have enough energy to break free from their fixed positions. Glass is an unusual solid. It doesn't have a sharp melting point. Instead, it gradually softens as it heats up. This is because the atoms in glass are arranged randomly. There's no defined structure for them to break free from. The temperature at which glass starts to soften is called the glass transition temperature. Gamma rays can affect this temperature. In some cases, they can make the glass transition temperature higher. This means the glass is more resistant to heat. Section 7. A universe of applications, from medicine to exploration. We've learned a lot about our special glass by blasting it with gamma rays. We've seen how it changes its elasticity, hardness, color, and thermal stability. But this is more than just an academic exercise. This knowledge has real-world applications. For example, this glass could be used in radiation shielding. It could protect sensitive equipment from harmful gamma rays. It could also be used in medical devices. Its biocompatibility makes it ideal for implants, and its ability to change color could be used in sensors or optical fibers. The possibilities are endless. As we continue to explore the universe, we'll need new and innovative materials. Materials that can withstand the harshest conditions. By understanding how gamma rays interact with matter, we can create these materials. And who knows what we'll discover along the way. The future of glass is bright, and it's filled with gamma rays. Hey there, science enthusiasts! As we wrap up today's episode, I want to take a moment to shine a spotlight on the incredible researchers making waves in the world of science. Today, we're diving into a groundbreaking study on the synthesis and physical characterization of gamma-irradiated cadmium phosphate glass modified by copper oxide. Now, I know that might sound like a mouthful, but stick with me because the minds behind this study are doing some truly amazing work. This research comes from the brilliant team of the Associate Professor Dr. Omnia Ibrahim Sallam, Professor Dr. Fathy Ezz-Eldin, both from the Radiation Chemistry Department at the National Center for Radiation Research and Technology, Atomic Energy Authority, Cairo, Egypt. And let's not forget the corresponding author, Dr. Ahmed Abdel-Daim from the Radiation Physics Department at the same institution. Their dedication and expertise have significantly advanced the field of optical materials and radiation shielding, potentially paving the way for future innovations that could impact a wide range of industries. Just imagine the possibilities. So, what does this mean for us? Well, their work could lead to improved safety in radiation environments, better materials for electronics, and even advancements in medical technologies. The potential applications are vast and exciting. But here's where you come in. I want to hear your thoughts on this research. How do you think this technology could be applied in the future? Leave your comments below, and let's get a discussion going. If you enjoyed this video, don't forget to like it, share it with your fellow science geeks, and subscribe to For Science Salah Lotfy channel for more cutting-edge discoveries.